Hello everyone, welcome to yet another episode of Tensor. We are continuing what we have learned in the earlier episode of Tensor, and we will continue with learning further intricate details on the tensor analysis. I've got a good amount of response for students who have looked into my video, so I'm very thankful to them. So this is the third part. We covered 2.0 and 2.1. Well, it would be a new topic of tensor that we will do. So let us start going with this particular topic of tensor. We will deal more with that, but before that we will just do a quick revision on what we have learned earlier. So this is basically, let us see what are the topics that we are going to cover in this particular video. So the topics that we are going to cover are this. We are going to see into what is finding values in a stress tensor. This part, we have done it earlier. We have looked into what a stress tensor is. We also looked into how to write the indices using a common easy method. So we are going to find the values in a stress tensor. We are also going to understand what are basis vectors and how the change in basis vectors causes an important change in tensor analysis. We are also going to look forward for forward and backward transformations. And finally, we will look into what is a Kroneckerdelta. So finding values in a stress tensor, this is a trivial example. It would be quite easy to understand. Basis of vectors, those who have gone through vector, which is a basic idea in physics, must know what is a basis vector. Change in basis vectors actually relates to forward and backward transformations. Forward and backward transformation is extremely important when we will go forward in understanding Einstein's general theory of relativity. You will see this transformation of the axis actually is important, and that is why we look into tensor and Kroneckerdelta. We won't do much with Kroneckerdelta, but that is how we would do. So that is basically comprising of the topics, and this is what we will going to cover in the video. So first, finding values, basis vectors, change of basis vector, the transformation of coordinates, and how it is related to Kroneckerdelta. So before we go ahead and we start with that, I would like to make a quick recap on what we have learned in the earlier video so that it becomes easier for you. Now I would like to tell you what makes a tensor unique. We have dealt with that, but I would still like to draw a kind of a quick revision. Tensor unique, right? So what makes a tensor unique? This is something where we will just do a kind of a quick revision on. Now, if you have seen in the earlier video, we have seen that we have two types of things. One is a vector, one is a tensor. So, for example, if I take a vector, so if I write this is a vector, so vector essentially have got two qualities. One is the magnitude, and the second one will be the direction. So any vector, say for example, if I take V as a vector and if I plot it in a graph, so what eventually happens is that if this is a vector V, right, and it is exerting a force of 2 newtons, then we can say that it is exerting a force of 2 newtons at an angle of 30 degrees. Exerting a force of 2 newton at an angle of 30 degrees. Now if you take a tensor, specifically if I take for example a stress tensor, then other than magnitude and direction there is another important thing which makes it unique. So let me tell you, one is the magnitude, right, this part. Second one would be direction, that is in which direction it is happening, and third one which makes it unique is called the plane of action. That is a plane of action. So vector cannot denote this. Stress tensor or a tensor which is denoted by T double line under it will be able to denote what is the plane of action. What do we mean by plane of action? We have noted in the earlier video, but still I would like to show you a picture. Say for example, this is a small cube, right? And X, Y and Z axis. Each of these cube 6 faces have X, Y and Z axis. That means a stress which is happening in X direction in X plane. y direction in y plane, z direction in z plane. In case that the indices are different, that means the stress which is happening in the plane of x but in y direction, in the plane of y but in z or x direction. So that is why this makes that in which direction x, y or z, and in which plane x, y or z. So that is what makes tensor typically important. So that is why I have written that stress has got magnitude, direction, plane of action. Vector has got only magnitude and direction. So that is how vectors and stress or tensor is a little bit different. So just a quick recap on the indices that we have written earlier. So I will just like to give you a quick idea on the indices that we have drawn. So let us say we have got here, so we have got tau xx, tau xy, and tau xz. This is just a quick revision. This is important. Then we have got tau yx. Then we have got tau yy. And we have got tau yz. Then further we have got tau in the z plane zx. Then we have got tau zy, and we have got tau zz, right? And this actually forms a kind of a stress tensor, right? So just note another thing, that this part, this is the diagonal, so it mentions all xx, yy and zz, which we have learnt in the earlier part. So what I would like to tell you, if I take out this part and write here as tau xx, okay, so this part of the indices, what does it denote? The plane on which stress is taking place, and this is denoting the error. So I can write here, this one is the plane and this one is the direction, right? So for example, if I quickly draw a cube over here, just to give you a basic idea. So I join this, just a very basic idea. So that means if I take this part of the cube, right? So this part of the cube has got x, y, so I may make it x, y and z. So in case if I take it out, tau xx, that means on the x plane, that is this particular plane, right, this one shaded one, the stress is happening on this plane, which is a x plane, and it is happening in x direction, right? This is the double, this dotted is y plane. So if I take out the say for example tau yy, that means, okay, let me put a different color, tau yy, that means that the stress is happening in the y direction. This is the y direction in the y plane. If I take out zz, that means, say for example this part, this stress, we also have got x, y and z. So if I take this one, that means tau zz means that the stress is happening on the z direction in the z plane, z direction, z plane. In case if I take out any abrupt number, say for example tau yz, what it means that the plane is happening in, the stress is happening in y direction, but in the y plane in the z direction. So if I got this one as y and this one x and z, so this is happening in this direction. This is the z direction. So tau yz means that it is happening in the y plane but in the z direction. So just note the first indices which determines the plane on which is happening. So yz means it is happening in the y plane but in the z direction. So second would determine the z direction. So similarly we can draw it something like this. Say for example, if I take a cube out, and if I make a kind of this x, y and z axis, right? So for example in the x plane only, so say let us say xz, that means it is happening in the x plane, z direction, x plane, x direction, x plane, y direction, right? Now another part which becomes extremely important in this is the diagonal part, this one, right? So as we have noted that the diagonal elements represents a normal stress. So let me just write it for you. So I can see for example diagonal represents what? It represents a normal stress. It represents a normal stress, right? And other than that, anything other than that, so I put it as other, any other, that means, say for example, xy, xz, yx, yz, zx, zz, this actually represents what is called a shear stress, right? It represents a shear stress. So what are the diagonal elements? Say for example, I can write tau xx, then we have got tau yy, then we have got tau zz, right? These are actually representing normal stress. Normal stress. So these are representing normal stress. And just to show you, courtesy goes to my wife. This is a nice little diagram, right? So this is showing the normal stress, and this is showing the shear stress. So what is the difference? I think we all know that normal stress actually happens in direction perpendicular to it, right? Shear stress is happening in the direction parallel to it, right? Yeah, this is a nice view. Yeah, so we can denote it by sigma. It is the force that is applying divided by A, which is the area on which is applying. So you see normal stress is happening perpendicular, shear stress is happening parallel, and same things happen here. If you notice in this cube, any stress we called it diagonal, xx, that means, see, it is perpendicular, yy, zz. These are all perpendicular. X plane in the direction of x is perpendicular, y plane in the direction of y is perpendicular, z plane in the direction of z is perpendicular. And this shows what is actually a shear stress just by an illustration. My wife drew it because I'm not good in this type of drawing. So this is normal stress which is happening perpendicular, shear stress are parallel, and this is the formula, right? So this is how we just calculate, we got the, so this is the force, and this is the cross-sectional area. If you want, I can just write it for you. So this is basically the force. This is the force, and this is the cross-sectional area. Cross-sectional area. So, and this is denoted by sigma, small sigma, force, F, A, the cross-sectional area. So this is the force, this is perpendicular, and this is parallel, right? So this is basically a kind of a basic revision on what we have learned, but it is important so that we can quickly know what is a shear stress, what is a normal stress, and how we can go about in calculating those shear stress and normal stress, and how through the diagonal part we can come to know that it is a normal stress and why it is so, because these are all perpendicular, which we have shown in the picture. Now we will come to another part of the video where we would be representing more or less what we called finding values in a stress tensor, right? Now if you notice, let me just show this part. If you notice in this part, we have all mentioned this xx, yy, zz, but it carries no value. Have you seen that? It actually carries no value. So what if we really want to put some value, I mean to say 1, 2, 3, 4, something like that, and we want to calculate the values of a stress tensor. So let me put out a kind of a basic heading over here. So what we would do is that we would be finding values in a stress tensor. In a stress tensor. So let us see that by finding out some very basic ideas, can we find out some very basic values or not. So what we do over here is that we will just draw this kind of a figure, a right angle triangle. Not a right angle, I would say it would be at 45 degrees, right? And okay, so we got this one is a perpendicular, this one is the height, and this one is the base, right? And this is cutting at an angle of 45 degrees. Say for example, I write it as 45 degrees, right? So now what happens is that we are going to find the sine theta. We are going to find the sine theta of this angle, which is equals to perpendicular by height, and which is equal to sine of 45. and which equals to 1 by root 2. I am taking a simple value so that I can just make you understand. In the same way, if you want to find the cos theta of this angle, it would be base by hypotenuse, so we put it as b by h, equal to cos of 45 degrees, and it would be the same 1 by root 2, right? Now what I will do is that we will take three normal vectors, x, which is this one. I am assuming this 1 by root 2. Then we take y, which is again this one, which is 1 by root 2. And because we don't have any z axis which is coming out of this way, so we take that z equals to 0. Right? We take the z equals to 0. Now what I will do is that I'm going to multiply this value. I will take a dot product of these with the stress tensor. So what eventually it will become is that x, which will be basically 1 by root 2, 1 by root 2 and 0, right? This would be the x multiplied by, or taking a dot product of the stress tensor. So you have to just bear with me until I write the values of the stress tensor. Tau xx, tau xy, tau xz. Then we have got tau yx, tau yy, and tau yz. Then we have got tau zx, tau zy, and tau zz. So I am just multiplying this with this. This is the stress tensor, right? So what we get is that we get a stress vector, which is denoted by S with an arrow. This is the stress vector. Okay, when we are multiplying, we are getting a stress vector, and this would be equal to. Okay, so what I am going to do is that I am going to multiply this one, tau xx, then I am going to take tau yx, then I am going to take tau xy, tau yy, tau xz, tau yz, right? We are ignoring this part because we don't have the z axis. So it would eventually become tau xx multiplied by 1 will be 1 by root 2, right? Then we will get a plus because we are adding these values. Then we get tau yx multiplied by 1 would be tau yx, followed by root 2, right? Then we will get the next one, that is tau xy. So that is tau, right? Tau xy multiplied by 1 would be same. It would be root 2. And then we add up tau yy, this part. Tau yy multiplied by 1 would be 1 divided by root 2. Plus comma, it would be then the value of tau xy, this one. So we have got tau xx, tau yy, tau xy, tau yy, and then we will get, yeah, so this one tau xx, tau yx, tau xy, tau yy, and then tau, we will get what, tau xy, xx, xyx, xy, yy, then we will get tau xz. We'll get tau xz. So we'll get tau xz followed by root 2 plus this one tau yz. Tau yz. This is tau yz. So we get tau yz by root 2. So this is what we actually guessed. So eventually what is coming up is that we are getting the values. This one is what we are getting, stress in x component. This is in the direction of x. This is in the direction of y. And this is in the direction of z. Right. So this is stress tensor in component. This is a stress vector, mind it, right? So we can put this down as a stress vector. So this is a stress vector, right? So we can summarize this particular formula. So what we can write out is a stress vector. So we can put it in this way. Say for example S, then an arrow. This is a stress vector equals to the stress tensor, which I can put it as t with two lines in the below with a dot of x, which is the normal vector. So I will just put the lines so that it becomes easier for you to understand. So this is a stress vector. So this is a stress vector followed by a stress tensor. This one is a stress tensor, and this is a normal vector. This is a normal vector. Right. So normal vector means that in the figure it would be something like this, which is, you know, pointing in this direction in x, right? So this is actually, as you see, that what we have done eventually is that we have taken xx, then we have got yx, or this part, then we have got xy, then we have got yy, then we have got xz, xz, and then we have got yz. So this actually is just a kind of an easy demonstration of if we take the values of sine over here as sine 45 1 by root 2, cos theta cos 45 1 by root 2, by simply multiplying or taking a kind of a dot product, we get the values of a stress vector. So this is stress vector equals to multiplied by stress tensor multiplied by the normal vector, which is the x vector. So dot product of a vector of a tensor, dot product of a vector and a tensor gets back to the vector. So dot product, here we are taking the dot product of this vector, that is the normal vector, and the tensor gives back to the vector. So if you want, you can just put it over here. We can write it something like dot product, okay, of a vector, dot product of a vector, in this case, see for example x, which is the normal vector, I can put it like this, okay, and a tensor, which is this one, t, this one, stress tensor, gets back to the vector, this one, s, stress tensor. So first part, this is where I'm going to take a pause because we will make it in 2-3 parts of the video. So what I would like to give a quick review is that, see, we are done with the first part, which is the finding the values in a stress tensor. We have done that. Before to that, what we have done, we have seen that how tensors can be unique, right? And what does the subscripts mean, that what does x and y means, diagonal and normal stress. We have also seen why xx and xy are called as the normal stress, because it takes in the direction perpendicular of xy and z axis. This is a nice diagram which shows what is normal and shear stress. So this is what is called a near normal and shear stress. In this diagram we have also seen that why it is happening in x, y and z. So each stress or each force which is happening in the direction and in the plane. And finally what we have drawn a kind of a small trivial simple example is that we have seen that if we want to find the values of a stress tensor, then how we can do it. We can just use the normal vectors, which is, I have done it as 1 by root 2 and 1 by root 2 and 0, and we have put it in the matrix of stress tensor and just got the values. So stress vector we get eventually is a stress tensor multiplied by normal vector. So that brings, and here I have written the summary. So that brings at the end of the video. We will be proceeding with the next video where we will cover up bases of vectors and change of bases of vectors and forward and backward transformations. So hope you like this video. If you have any question, you can put on there, and till then, goodbye and have a nice day. Stay safe and do stay happy. Thank you very much.